Welcome to Crypto 101, a first principles jargon-free course on blockchain and its impact on financial services. We are in the process of learning how cryptocurrencies mimic the properties of fiat money. We are currently focused on the property of transferability by which fiat money is transferred from one account to another. In this lesson, we will learn of the final step of value transfer, namely the formation of the blockchain. We will also learn about soft forks and how soft forks are resolved using the longest chain rule. Before we proceed further with this lesson, let us take a moment to orient ourselves on where we are. We have been learning about how cryptocurrencies mimic the four properties of currency. The property that we are currently focused on is transferability. In a previous lesson we learnt that cryptocurrencies are transferred via the three steps of initiation, authentication and value transfer. We are currently covering the final step of value transfer. Before proceeding further, let us recap the functions performed by the nodes. First, is transaction verification. The purpose of this function is to authenticate individual transactions. Second, is mining or transaction confirmation. The purpose of this step is to batch transactions into blocks for the purpose of updating the official record of the blockchain network. Third, is block verification. The purpose of this step to independently validate the block propagated by the successful miner. There is a final step, which is adding the block to the existing chain of blocks. In this lesson, we will learn about this final step. Each new verified block is added to a chain previously verified blocks. Consider block 1 that was the very first block ever mined and verified. Each block gets added to a chain with a unique identifier and references the identifier of the preceding block. The resulting chain of blocks is called the blockchain. So, now we know how the name blockchain is derived. We will now learn the mechanics of how a chain of blocks is formed. To keep things simple, we will assume that there are 6 nodes. 3 nodes are mining nodes. We will call them M1, M2 and M3. 3 nodes are regular nodes. They don't mine but only validate transactions and blocks. We will call them R1, R2 and R3. Assume there are 4 blocks in the chain. At this point both M1 and M2 are successful in forming blocks within a few seconds of each other. We will call the block mined by M1, the red block. We learnt in the previous lesson that the block header of each new block must have a reference to the previous block. Hence, the block mined by M1 references block 4. We will call the block mined by M2, the blue block. The block mined by M2 references block 4 also. We now have 2 blocks mined near simultaneously. The red block and the blue block. Many of the transactions within the 2 blocks are the same. Both blocks reference the same parent block, which is block 4. The miner M1 adds the mined red block to its version of the blockchain. The miner M2 adds the mined blue block to its version of the blockchain. The 2 nodes propagate their blocks to the other nodes. R1 receives the red block first. It validates the node and adds to the blockchain. A few seconds later it receives the blue block. Since the blue block references the same parent as the red block, R1 rejects it. R2, like R1, receives the red block first and rejects the blue block. R3, on the other hand, receives the blue block first and rejects the red block. Mining nodes also perform validation function. Hence M3 also receives the mine block. On receiving the mine block, M3 realizes that it has lost the current round of mining. Like R3, M3 receives the blue block first and rejects the red block. Now we can take a snapshot of what the blockchain looks like in each node. Some nodes have the red block and some have the blue block. We can call them chain red and chain blue. Miner 1 is on chain red. Miner 2 is on chain blue. Miner 3 is on chain blue. R1 is on chain red. R2 is on chain red. R3 is on chain blue. There is a lack of consensus among the nodes at this point on which blockchain is the official set of records. We can now get introduced to a term called block height. Block height refers to the number of blocks preceding a block. Normally, there should not be 2 blocks at the same height. But in our current scenario, both red and blue blocks have the same height. Next, we will see how this anomaly resolves itself. Now the next round of mining begins. Miner 1's candidate block references block red as parent. Miner 2's candidate block references block blue as parent. Miner 3's candidate block references block blue as parent. Miner 3 wins the game of chance. Let's call the block mined by Miner 3 as block green. Miner 3 takes block green and adds it to chain blue. Miner 3 propagates the green block to the others' nodes. M2 and R3 have no problem. They are already on chain blue. They receive the block from M3 and see that the parent block is blue. This makes sense to them. Hence, they simply extend chain blue. M1, R1 and R2 have a problem. They are on-chain red. Hence, they would expect the latest mined block to reference the red block as the parent. But the latest mined block is referencing the blue block as parent. M1, R1 and R2 will now be seeing two chains. Option 1 goes like this. Block 1, 2, 3, 4, red. Option 2 goes like this. Block 1, 2, 3, 4, blue, green. Since each node is independently keeping records, how should they choose? The network rule is that the nodes always choose the block with the greatest cumulative proof of work. Option 2 has the greatest cumulative proof of work since it represents the cumulative work on 6 blocks as opposed to 5 blocks in option 1. The network rule is that the nodes always choose the block with the greatest cumulative proof of work. By the longest chain rule, all the nodes will switch to longest chain and the discrepancy among the nodes will resolve itself. It is as though block red never existed. Block blue wins. But what happens to transactions in block red? We can think of the transactions in block blue and block red as a Venn diagram. All transactions in Zone 1 and 2 are already in the blockchain. Zone 3 transactions are the ones that get pushed back into the mempool and queued up again for mining. Block red is what is called a stale block. A stale block is a block that was successfully mined but could not be part of the official blockchain record because of a competing block that was mined near simultaneously. In the Bitcoin blockchain, the miner of the stale block does not earn any block reward or transaction fees. However, we will learn later, this is not true of all blockchain networks. Let's go back to the point when the blockchain had two different versions. Some nodes were on chain red. Some nodes were on chain blue. At this time the miner 3 came along and mined block green on chain blue. But what if at the same time, another miner came along and mined block brown on chain red simultaneously? The discrepancy would continue till the next round of mining. While theoretically possible, it is rare for this to happen. The simultaneous mining of blocks is itself rare and the probability of this repeating itself is exceedingly low. Most discrepancies resolve itself within one round of mining. We can now introduce a new term called the soft fork. A fork refers to a scenario in the blockchain where multiple versions of the blockchain exist simultaneously. A fork is soft when these multiple versions reconverge to one version through the normal operations of the blockchain network. The example that we just reviewed was a soft fork. The use of the term soft fork suggests the presence of a hard fork. We will cover hard forks in a later lesson. A term that is often used within the context of blockchains is consensus. Consensus refers to the agreement on one set of records, as the representation of truth, by all the nodes on the blockchain. If you calculated the Bitcoin balance of any address, you should get the same answer no matter which node you looked at. What data record, specifically, is being consented to? First, all nodes agree to the content of each transaction. How much was paid? What was the digital signature attached to the payment? Second, is the sequence of transactions within a block. Finally, all nodes agree to the sequence of blocks, though there may be temporary deviations from consensus because of soft forks. Consensus mechanism is the mechanism by which agreement is reached. The consensus mechanism in the Bitcoin blockchain is twofold. First, proof of work mining, which stipulates that the content of transactions within the winning block and the sequence of such mined blocks reflect the truth. Second, the longest chain rule that stipulates the chain with the highest cumulative proof of work represents the true sequence of blocks. We have covered a lot of material and hence, before proceeding further, it is useful to pause and reflect on what we have learnt regarding transfer of cryptocurrencies from one account to another. In the concluding section of this lesson, we will do precisely that. We are currently in the process of learning about how cryptocurrencies mimic the 4 properties of fiat currency. We are currently focused on the property of transferability and the 3 steps by which cryptocurrencies transfer between accounts. In the payment initiation step, a payer creates a payment message and attaches a digital signature to it. This step can be done offline. The transaction is then broadcast to the blockchain network. In the payment authentication step, transactions are individually verified by each node. This involves, among other things, checking whether the payer's UTXOs support the payment being made and the digital signature is valid. However, authentication of the transaction is not sufficient for value transfer. The transactions need to be confirmed into blocks by a mining node. The blocks, in turn, need to be validated by each node. The blocks are then added to the blockchain by each node. If there is conflict between the chain of blocks, the longest chain wins. In the traditional system, the bank account of the sender and the bank account of the recipient are held within the databases of 2 banks, each of which is a walled garden. Payment rails are needed to connect them. Imagine if instead of a payment, Alice was sending a package to Bob. The package could be transported to Bob via road, air, ship or rail. While Alice may not know which modes of transportation the courier company used, she feels the impact in terms of cost and delivery time. Payment rails are analogous to these transportation methods. While the starting and ending points are two bank accounts, the rails by which the transfer of value occur may be different. These rails are independent of whether Alice is making a payment as a consumer or in a business capacity. Examples of payment rails in fiat money include wires, ACH, real-time payments, checks, cards and correspondent banking. Learning about these payment rails is outside our scope. However, we will spend a couple of minutes on understanding why payment rails are required in fiat money. Bank account data is recorded in walled gardens of individual banks. If you were transferring within the same bank, the bank just does a book transfer. Payment rails are not required. But if the payer and beneficiary bank are not the same, a neutral third party is often needed to connect them. This almost always includes central banks. But private entities in the form of payment network operators like MasterCard and Visa play a role too. When we are transferring cryptocurrency from one blockchain address to another, there is no need for payment rail. This is because the information on source and destination blockchain address exist within the same set of records and is replicated in each node. No third party is required to connect the source and destination. We have been learning about how cryptocurrencies mimic the four properties of currency. The property that we focused on in this and last few lessons is transferability. With this lesson, we have completed the discussion and ready to move on to the final property, which is the inability to double spend. But before proceeding to the next lesson, review the summary of this lesson. See you on the other side.